In this video, we would like to talk about two methods, BruteForce and exhaustive search. It's a very intuitive method. Let's take a look. First, let's take a look BruteForce. What is BruteForce? It's a straightforward approach, usually based directly on the problem statement and definitions of the concepts involved. For example, computing a to the power of n, computing n factorial, multiplying two matrices, searching for a k of a given value in a list. For example, the first example, let's say a to the power of n, and very easily we can write the pseudocode to calculate that, right? A is larger than 0, n is non-negative, and since n it is the parameter, and a it is the constant it gives. And for example, let's say we want to do calculation exponential, right? Let's say algorithm exponential. And we have two input, and a and n, right? So take a look at this one. This calculation very easy, right? You give n, then you want to have a multiple a. We product a for n times, and such that we can easily to write the loop. We see the beginning we have results signed to be 1, and we use a count variable I signed to be 1, and scan the I from 1 through n, and every time we have result signed to be result times a, right? Okay, so this is the solution. Let's take a look at another one. Multiply two matrices, right? This is multiply two matrices. Based on the definition, let's say A, n times m dimension, times B, m times l dimension. This is supposed equal to a I equal to what? Let's say it's equal to n times l dimension, and each element here corresponding to, let's say we use a C to represent. We have Cij, right? And each element has been represented as Cij, and I from 1 through n, j from 1 through l. And we see Cij is equal to here Ai T B T J, right? And I is from 1 through, here we should be used T, right? T is equal to 1 through m, and you see this A, what corresponding A, and we say A n times m is equal to A Ij, right? It's n times m, and B m times L is represent times L, right? It's a matrix, and each element we use A to represent, and we say A times B equal to this Cij in the specific matrix which has the dimension n times L. Each element we use Cij to represent. Based on this definition, we can quickly to write. We can write the pseudocode. We say for I from 1 to n, for j sign initialized to be 1 to l, and we want to do calculation. We say here first we need to assign the Cij equal to 0, and we say for t initialized to be 1 to m, we have a Cij signed to be Cij plus we see AIT times BTJ, right? Okay, this one corresponding to the matrix, right? We see Cij, which corresponding to Ci, this one, right? Two-dimensional array. And also AIT here corresponding to AIT. And the BTJ corresponding to TBTJ, right? Okay, very good. So I think this is give us very good examples to say which kind of problem we can easily to use brute force. And then we want to, since we want to compare the different methods, or by giving the same problem. Let's check a sorting problem. The sorting problem corresponding to, let's write down the mathematical definition. Okay, the sort problem. Or let's see, sorting problem. We see given a sequence of numbers. It could be given sequence of objects, right? And each object can be compared to each other. So for simplicity, we use numbers. Given a sequence of numbers, A1, A2, AN. To what? To find let's write it down. To find a permutation, or we can call that reordering. Let's define it: A1 prime, A2 prime, and AN prime, right? A1 prime may equal to A1, may not be, because it is reordering of the input sequence such that with A1 prime smaller than A2 prime smaller than AN prime. If we define this sequence as S, let's see, this is S, right? If we define this one as the S, let's erase a little bit. Is S equal to this sequence? Then in that case, we can define this one to be S prime. We want to give a sequence S. We want to find the permutation of this S, and such that each element in this permutation is in the ascending order. This is the question we ask. Intuitively, since you would like to find it this order, right? Intuitively, we say intuitively. And we would like to find elements in correct location. Right? For example, we want to find, let's see example, right? We want to find the largest guy. Second largest guy, right? Or third largest guy, right? Once you find this largest guy, or second largest or third largest guy, we put in the specific location, right? So the largest guy here, suppose this should be an prime. This should be an minus 1 prime. It's an minus 2 prime, right? Then we just place it in the correct location. Or you just find the smallest guy, and find the second smallest guy, find the third smallest guy. This is very intuitive thinking. This is go to what we talk about, selection sort. Selection sort, we go back to slides. Scan array to find its smallest element, swap it with the first element, then starting with the second element, scan elements to the right of it to find the smallest among them and swap it with second elements. This is corresponding to what we talk about. Find the smallest element. We wanted to find is S prime and A1 prime corresponding to smallest long bone. And A2 prime corresponding to second smallest, right? And A3 prime corresponding to third smallest. This is the question we ask, right? And then from the remaining one, we want to find each smallest one and we place that in here. Let's go to this source code. Let's go to this solution. Let's take a look at example. If given 7, 3, 2, 5, and we wanted to reorder them, right? We want to use the permutation. We want to use this selection sort. The question for you, when we talk about this example, the question for you is how to write the pseudocode. So the first step from here, we give a list, find the smallest one. This is easy to do, right? And we find 2 is the smallest one, and we replace these 2 with the first elements. We swap them, and then we have the first iteration, first one. We find with 7, 5, right? We find the smallest one. We fix the smallest one. Then later, from the remaining one, we find the second smallest one. And if it's not a specific position, then we have to swap with the second element. So we have 3 will be here, 7 will be here, right? 5 will be here. Then next step. So this is step 1, big step 1. This is step 2. Then later we want to find the third smallest one and swap it with 7. Then we have this, right? So this is the third big step. Then later step we just place with the 7. Okay, so now let's take a look at the pseudocode. And since we want to find the smallest element in the remaining sequence, in the beginning is the whole sequence, and once it meets the last guy, we do not need to compare it anymore because the last guy, of course, is smallest compared to itself. And such that we have count variable I from 0 through n-2. In each iteration, we want to find the smallest one in the remaining subsequence, right? So this is the for loop. Is for loop. In this for loop, in each iteration, we find, let's say, for i's iteration, I think maybe this is, let's use the nodes is cleaner. Okay, let's see the idea here. For i's iteration, or let's see, this is in i's iteration, we want to find i's smallest element, right? And this I should go from I. This I is for I equal to 1 to n minus 2, right? In each iteration, this is what we would like to find. And to work on this common, and we can see here, we define the smallest, or in this case, in this code, we define the mean. We say the mean is assigned to be specific current element, right? And we see for j equal to I plus 1 to n minus 1, what we want to do, we say we want to find if the current element, if a j, it is smaller than a mean or not, right? If it's true, we remember this j, remember this location, and such that we can swap a j, not a j, because j always change with a mean and a I, right? And since we know such case, we finish. Now the question is, what is the time efficiency? What is the time efficiency here? What is space efficiency? And what is stability corresponding to? Because this stability, we will explain that later. Time efficiency, this is what we discussed in the previous, in the previous video. And with the time efficiency, we have to check what is the input. Let's write it down in the notes. So let's check for time efficiency. First, with the time efficiency, we have to check we have followed the steps, right? First, decide the input size. What is the parameter for input size? In this case, of course, it's a length, right? Let's use n to represent. And the second one, decide basic operation. This basic operation related to elements of the input, right? And also, it make biggest contribution to this algorithm. And take a look at this one and tell us what is the basic operation. In this case, we see the out loop, inner loop, and this is the is comparison, which it will happen in the outer loop and also inner loop. It will make a biggest contribution. We use this one to represent the most time consuming statement. We use this one to represent the upper bound of our the boundary of our time complex lattices. Then after that, we count the frequency of the basic statement being invoked, right? Then we see that based on the previous video, we see that usually we like to use a formula to do the summation. So we see here we have I equal to 0 through n minus 2, right? And we see even if you do not just count for basic operation, you have 1 plus this one, right? You have I j equal to I plus 1 through n minus 1, and you have a comparison. This if statement, right? If you say if body, this is depending on this is true or not true. But comparison statement will definitely be invoked, and this is finished. Then we plus 1, right? And we see in the previous one, we see we can ignore lower cases, lower order term, right? So now let's write it down here. So we have 2 plus j equal to I plus 1 n minus 1 is 1, right? And we follow this one, we could put this, we can separate them. So we have I equal to 0 through n minus 2 is 2 plus I equal to 0, n minus 2, j equal to I plus 1, n minus 1 is 1, right? And then we say here, this is constant, and in how many times it got invoked, and this is times n minus 1 plus, and we do this calculation first. This is constant, and we have I equal to 0, n minus 2, we have n minus 1 minus I minus 1 plus 1, right? Okay. Let's count how many times, right? So this reason we need to have plus 1. So it's 2n minus 2 plus, and let's finish that, n minus 2, n minus I minus 1, right? And this doesn't depend on this I, so this reason we can have 2n minus 2 plus I equal to 0, n minus 2, n minus 1 minus n minus 2i, and such that we have plus this n minus 1 times n minus 2 plus 1, right? And minus, and here this is the I from 0 through n minus 2, so we have 2 times n minus 1 times n minus 2, minus 2 here, right? 2 here. Okay, so let's see, we rewrite that. Let's see, we rewrite that, make sure it's clear. Okay, so minus, this is corresponding to what? Corresponding to 0 plus 1 plus 2 plus n minus 2, right? So this is equal to 2n minus 2 plus n squared minus 2n plus 1, right? And then minus, let's see, this is corresponding to this, we need to do calculation. So this is have n minus 2 times, right, n minus 1 divided by 2, and this is equal to to 2n minus 2 plus n squared minus 2n plus 1, and minus this is corresponding to, let's say, half. This is corresponding to, right, this part can be replaced to half of n squared minus 3n plus 2, right? And so it's minus n squared plus 3n minus 1, right? Then in total we have n squared plus 3n minus 2, right? And we see that based on the big O notation, we ignore lower order term. This is lower order term, right? This is also this is low order term. We need to ignore this no order term. We ignore that. And we also ignore the coefficient, we ignore, and such that we have n squared. So this is term efficiency analysis for this selection sort. Okay, that's good. And then the space efficiency, in this case we only need to have an array. This is let's write down here. This one is n squared, and this is O(n), right? The stability corresponding to the after you sort this, after you sort the sequence, rearrange the sequence, and the first, if they appear, if some elements has the same value, you want to make sure in the original sequence, in original S sequence, after the rearrangement, the location which for duplicate the values should be follow the same order. So if A1 and if A1 is the same value as the A2, we would like to see A1 prime is no. We would like to see the elements stay in the smaller location and also appear in the smaller location of the S prime, right? So this is stability corresponding to you don't want to, if the value is the same, you want to make sure the location to stay keep the same order, right? The index keep the same order. You don't change the order of the index if the two values are the same. Okay, then let's go to the next one. Another usage is a string matching, which corresponding to give you two strings. For example, one pattern as a pattern string, a string of M characters to search for, and also give you a text is a longer string of N characters to search for. So in this case, M is smaller than N. We want to find a substring in the text that matches the patterns. For example, it's also going to the quiz question. Let's see example. Let's use this one as example. So we would like to, given the pattern 001011, given the text 100101011, right? And we want to find out this pattern exists in text or not. In this pattern, we have a M character, right? We use this M character to map to, so here we have 6, right? We use this 6 character, we map to specific elements in the text, starting from location 1, and if we cannot find that, we go to the next location, We use this way to try to find first matching of the pattern in the text. For example here, right? The happy. And we want to find happy in the text words. And so in such case, you should have 5 characters. And we scan 5 characters from the 0 location to 1 location, 2 location, and here we find the first character, which is the same, first sequence of characters is the same as the pattern. And so, the steps for this brute force algorithm, first step is to align pattern at the beginning of the text. Move from left to right, compare each character of the pattern to the corresponding character in text until all the characters are found to match or a mismatch is detected. Where the pattern is not found, the text is not yet exhausted, realign the pattern 1 position to the right and repeat step 2. And in such case, the algorithm, you can imagine it's easy to write the pseudocode. Since we want to map these M characters to each location until the exhaustive search the text corresponding to, if we have N, let's say if we have N characters, and the last map, it is mapped to here, this should have M, right? M characters. The location of the beginning of the last map corresponding to N minus M. Okay, so this reason we want to map these m characters with the elements starting at the first position, right? And until the n times m position. So this is go to the outer loop. Then in each iteration here, we want to check this what we have the m characters in pattern exactly same as the m characters in the text or not. So we use j to represent the location of the m characters in the pattern. There is a count variable, count location in the pattern. And we check from 0 through m, and every time we check does these elements in the pattern at j's location equal to the element in I plus j's position or not, right? If it's true, we continue to check the next position in the pattern, and until we finish. Then in that case, we find one, we return j. We return I. If j equal to m, it corresponding to we scanned each element already in the pattern, and we found the exact matching of each character of the pattern with the some specific subsequence in the text. And or else it means we didn't find that, and then we have to realign these m characters to the location right to the previous the location. And from here we can check the efficiency, and this efficiency we can see, we can take a look to check for each statement. So in this one, this is a loop, right? It's a loop. And we can write I equal from 0 through n minus m. It's not so nice. Let's write it down here. Okay, so this is we check for string match. Time efficiency. Okay, so we take a look at the code, right? So this is for I equal to 0 to n minus m, do j equal to 0, well, j smaller than m, and p j equal to t I plus j, right? And if that is true, and increase j, or else we finish map these m characters to some position in the text. So we say if j equal to m, return I, or else we finish -1. And we see when we check the time efficiency, we take a look each line. And we know first we know this is the array length, the n, right? We need to check the input time efficiency, and we check input size. And the input size here we have n, we have m. Depending on this n, depending on this m, we choose both. And then we check for basic operation. Some of you maybe don't like in this way. In that case, we just count frequency. Let's just write in this way. And such that, let's see here, since we count the frequency, we say I equal to 0 through n minus m. And here, this statement, j, this is j assigned to be 0, right? One statement. And this while loop we check here. This really depending on the elements is equal or not equal. And we see if that's the best case, the first element, if the best case, first element, the first m characters happen to be pattern. In that case, it is you just need to have m. The runtime is m. But in some way, if the pattern not appear, if the pattern doesn't appear in the text at all, in that case, it is you have to check for all the check for each characters in the pattern, right? So let's use this one. So this is j from 0 through m minus 1, right? And this is j, and in that case we have a comparison statement and also increase statement even for this one. You usually have 3 statements here, right? And after that, it is, if you finish it, return, or else you have one more statement, right? This is we check for worst case. This is the worst case. And we see the best case corresponding to best case. If it's best case, you just need to check for, this should be, OM, right? Okay. Then in that one, you can continue to do calculation. And this is I, and we can ignore lower case, right? Only this one, depending on what we have, the m, this input size, we can ignore this one. So we have in minus m and j equal to 0, m minus 1, 3. And since this is constant, and we could have x equal to 0 to this minus 1 and minus m and minus 1, and here you could have 3 times m, hold on, yeah, m, right, 3m, and then since this is 3m, doesn't depending on your I, and we can directly to do that, is 3 times m times n minus m, right? And in that case, we have O 3 nm minus 3m squared. And we ignore the coefficient, and we see n larger than m, right? In that case, the runtime here, Tn, the worst case, is equal to ONM. And we see T best case, and here it's equal to OM, right? Because here the best case corresponding to the first, let's see, it happened, the first M character in text is a match of pattern, the given pattern, right? Okay, that's good. So now I save it. Okay, so this is the time complex analysis for string match. I think we can continue. And this is another one for polynomial evaluation. This one I put in the quiz question. So this is a polynomial function, and one of the way it is, and you check, because you check each subterm, you calculate each subterm and then do the calculation on that, right? So it means you scan I from n through 0, and in each inner loop, you calculate for one subterm, right? Since you have x times x to the power of I in the ith loop, we have to calculate x to the power of I, and this is a is inner loop, its goal is for calculate x to the power of I, and this one is calculate the specific ith term and sum up to the p and return to p. And this time efficiency in this case, and you can see even we do not have if statement, it exactly which correspond to what? So this is the, if you count that, is I equal to n from 0, and this is the j from 1 through I, right? And you count for 1. And you will see this is equal to n square. Okay. Another way it is, and people think about, can we reuse this calculation, right? Because you have p is equal to a n x to the power of n plus, if this is n, right? And plus a n minus 1 x n minus 1 plus a 2 x 2 plus a 1 x 1 plus a 0, right? So we want to reuse the power of the x to the power of I, for example, right? So in that case, it is this corresponding to, in each loop we calculate, for example, calculate this one first, and then we calculate this one, and every time we reuse what you calculated in the previous, the x term. And so such that once you change this solution, the efficiency here corresponding to big O(n). Another question we also use for divide and conquer, which is to find the closed pair problem. Find the two closest points in a connection of n points in a two-dimensional. For example, let's see here, right? So if we have multiple points and we want to check which two is more close to, which two is more close, this one or another one, right? So in that case, we have to calculate the distance intuitively. So we have to calculate the distance of each pair. Right? So if we have n points, given n points, so we will have, if we give n points, then we will have, give n points, we have n choose 2 pairs, right? And then it means for every pair, we have to do this calculation. And by this definition, by this problem description, we say in this algorithm, we check each pair. And then the runtime for this one is O(n squared), right? And this is the algorithm we can list. This algorithm we could have, and for based on what we have the description. So we have n points. Each point have x1 and xi and yi, right? And then we want to check and each data points, what is distance with another one. So you check, this look like, let's see, we have P1, P2, P3, right? We have Pn. And you want to check the distance between this one with Pn, right? So in that case, you check what is distance for this, P1 through Pn. And since the distance, it is symmetric, you don't need to do calculation here, right? No, the whole thing here, no. We have to check the distance between this element with that. So with the another elements, so this reason we form for I equal to 1 to n minus 1, do check j from the I plus 1 to I. And for each and j, each pair to the the index I and index j. We calculate the distance. If distance is smaller than the smallest one, then we remember what is this one, right? And in such that in the end we check for each pair and calculate the smallest one. Take a look at this one. We can very easy to see the time efficiency is n squared, big O n squared, right? And another question it is how to make it fast. Can we make it fast? Let's go to the next video. And so we said in this video we emphasize the brute force method. We check for different problems, sorting problem, string match problem, and closed pair problem. And this method, the strength of this method it really does have wide applicability, and it's kind of very simple to write code. It's reasonable algorithm for some important problems. But the weakness it is sometimes it really do not give you very efficient algorithm, and sometimes quite slow and acceptable slow, and not as constructive as some other designed techniques. Exhaustive search it is also brute force solution to a problem involving searching for element with a special property using among combinatorial objects such as permutation, combination, or subsets of a collection. And in this method, we want to generate a list of all the potential solutions to the problem in a systematic manner, evaluate potential solution one by one, disqualify the infeasible ones, and for optimization problem, keep track of the best one found so far. When search ends, allows the solution found. And the most important it is we need to scan all the possible solutions. So we have to check all the possible solutions, and in that case sometimes it's go to the exponential. For example, here is one of the example. It's called the knapsack problem. We will check this problem, go back to this problem again with a lot of addition, and we can use the dynamic programming and greedy algorithm to solve. In this video, we want to check the original one. Given n items, for example, you want to go for trip and you only have one big bag and you want to carry with n items, and each items which has the weight for each item I. So we have a weight I, we have value I, and the constraint it is in this bag. We need to make sure all that we carry on the things together, they are not more than, the weight is not more than W is constraint, right? And find the most valuable combination of items that you can carry with you that fit into the knapsack. For example, in this case, we have a capacity W equal to 16, and for each item we have the weight and also have the value. We want to find we want to maximize the value, the total value we pick up, right? Total value. Subject to, this is the object function, and subject to the content we select, the items we select, right? For example, if we select, we want to make sure the item we select, let's see, we have AI and the weight I, and if we sum up them, it should be smaller than W, right? W. I think we use the laws make it clear. So this is the knapsack problem. As a formula as mathematic and computational problem, we say given n items, right? Given n items, let's say we have give n items. For give n items, each item ai, let's say item I, let's see here, give n items, ai equal to two values, right? wi and vi. This is what we have. That makes sense, right? And here we also have I smaller than n, larger than 1, right? And the question it is, this is one condition and capacity, you can see here, and to find a selection such that find a selection and such that the sum of ai, if that is selected, let's use s to represent selected. If this one is selected, the value sum up from 0 through 1 is maximized, and I equal to 1 n s1 wi smaller than w, right? And w is given 1. So this is a formula of this, knapsack problem. Okay, and then in that case, it is we have to check all the possible cases and find the optimal one, the smallest one, right? And think about, if this is a given example and what could be specific case. Okay, this is what we have. So now let's see here. We have item 1, 2, 3, 4. This is W, this is the value, this is 2, this is the 20, 5, 30. This is a 10, this is a 5, 50, and 10, right? If we said we choose this 2, if 1 and plus 2, then in that case we have a value 50, right? And then it is the weight, it is 7, and it means we can add more, right? And if we have 1, 2 plus 3, then the value it is 100, but it is 17. So if the 10 is what we have, we cannot choose this one, but we could choose this one, and it could have multiple cases to satisfy for that. And so this is corresponding to, we consider all the possible selection. We select 1, right? We from the n, we select 1, plus n select 2, so n select 3, plus, and even we select all. So in that case, it's O to the power of n. This is the time efficiency for the knapsack problem, right? If we write it down here, so it means we need check all the case, right? Check all the combinations, the selection, all the possible selection. And find a best one. So this is the question for us, right? So in this one, corresponding to, we have the n choose 1 plus n choose 2, because we choose 1 is a full item. We choose 1 to check, choose 2 to check, right? It's choose 1. And this one, we can choose 2 to check. For example, 1, 2, 1, 3, 1, 4, 2, 3, right? And it's continue, we can have odd selected. With this one is go to the equal to 2 power of n minus 1, right? So it's exactly to the power of n, big O, to the power of n. Okay, so this is the Kippersack problem. We have another problem, is assignment problem. In this case, in this question, we put in the quiz, the n people who need to be assigned to n jobs, 1 person per job. The cost of assigned person I to job j is Cij. Find assignment that minimize the total cost. So we have a person, we have jobs. The algorithm plan generate all assignments, computed its cost, and select the cheapest one. How many assignments are there? Post the problem, ask the one about the cost matrix. So in that case, we need to make sure in each row we have 1 selected, right? If we select this one, and in another row we cannot select anymore. So we need to select this one, for example, right? So you make sure each row we have 1 value has been selected, and each column we have a unique one selected. And in such case, we could have multiple assignments and check for each assignment to see what is the best cost. And for this one, if you take a look, you'll find out in this also exponential cases. And with the exhaustive search algorithm run in realistic amount of time only on very small instances. In some cases, there are much better alternatives. For example, shortest path, minimum spanning tree is we would like to cover, and also assignment problem, and for specific specific context. In many cases, exhaustive search or its variation is the only known way to get exact solution. I think that's all for this video.